Tonight, we explore a quiet mystery that continues to shape how we see the world. The universe is vast, and much of it remains hidden from view, not because it isn't there, but because it lies just beyond the edge of what we understand. Let's begin. Right now, in this moment, you exist. But lean in closer, because the story of how that became possible starts in a place where even now had no meaning. Close your eyes for a moment. Let the world around you soften and fade. Picture absolute nothing. Not the simple darkness of a closed room or the quiet of a midnight forest. This is something far deeper, far stranger. No space at all, no width, no depth, no direction. No time to mark a beginning or an end. No light, no shadow, no possibility of movement or change. Just the complete absence of everything that could ever be named or imagined. Most people feel their mind pull back from this thought almost instantly, like fingers recoiling from a flame. The idea is unsettling, almost unbearable. Yet every attempt humanity has ever made to explain existence begins right here, in this vast and uncomfortable void. Long before written records, before cities or temples, people gathered around fires and tried to give shape to the same emptiness. In the ancient cities of Mesopotamia, priests and poets told of a time when only the primeval waters existed. Apsu, the sweet, fresh water, mingled with Tiamat, the bitter salt. Their union was restless, chaotic, formless. You can almost taste the brine on the air, feel the heavy stillness of an ocean with no shore, no waves, no horizon. Nothing stirred until conflict arose within the depths, and from that tension the first gods emerged, violent and alive. Farther north, in the cold lands of Scandinavia, storytellers spoke of Ginnungagap, the great yawning void between realms of fire and ice. To the south lay Muspelheim, where flames crackled endlessly. To the north stretched Niflheim, layers of frost and mist. Between them lay perfect silence, an immense gap where heat and cold held each other in perfect balance. Imagine standing there, the faint warmth on one cheek, the biting chill on the other, the slow drip of melting rime as the first giant took shape from the meeting of opposites. In the ancient texts of India, sages contemplated Brahman, an eternal reality beyond being or non-being, beyond description. From this breathless unity arose the golden cosmic egg, the Hiranyagarbha, floating motionless in the void. Inside it, everything waited. Outside, nothing. When the egg finally cracked, the universe poured forth like a long-held breath, finally released. Across vast oceans, in the red deserts of Australia, Aboriginal elders have passed down songs of the Dreamtime for tens of thousands of years. In that era, the earth lay flat and featureless. Ancestral beings slept beneath the surface, dreaming. No sun crossed the sky, no rivers cut the land, only potential, coiled and waiting. Then the ancestors awoke. Their footsteps carved valleys. Their songs called forth plants and animals. Their breath scattered stars across the night. These stories arose in isolation, separated by mountains, deserts, oceans, and millennia. Different languages, different landscapes, different lives. Yet each one circles the same impossible moment, the shift from absolute nothing to the birth of everything. Water gives rise to gods, ice and fire birth giants, an egg hatches reality, dreaming ancestors shape the world. The imagery changes, but the core remains unchanged. Something emerges where nothing was. Pause here. Let the quiet stretch around you, because something extraordinary lies hidden in this pattern. Cultures with no way to communicate described the same transition in strikingly similar ways. They sensed a profound stillness giving way to motion, absence yielding to presence. They felt the same unease beneath it all. How could intuition, unaided by instruments or mathematics, reach so far? Centuries passed, tools improved, observations sharpened. In the 1920s, Edwin Hubble sat night after night at the Great Telescope on Mount Wilson, measuring the light from distant galaxies. He noticed their spectra were shifted toward red, stretched longer the farther away they lay. The universe was not static. It was expanding in every direction. A quiet Belgian priest named Georges Lemaitre followed the implications backward. If space is stretching now, it must have been smaller in the past, denser, hotter, until, at some finite point, everything occupied a single, incredibly dense seed. He called it the primeval atom. We traded ancient myths for modern equations, gods and monsters for particles and fields. Yet the question at the heart of every story remained exactly the same. Why is there something rather than nothing? Whatever path you follow, science, faith, or quiet wondering, you stand connected to every human who ever gazed upward. From the earliest campfires to the latest observatories, we return again and again to the same edge, listening to the same silence, asking the same ancient question. And the silence, so far, has offered no answer. They called it the Big Bang as a joke. But the joke was on everyone who thought the universe had always existed forever. Imagine a modest patent office in Bern, early in the 20th century. A young clerk named Albert Einstein spends his days reviewing inventions, but his mind wanders far beyond the paperwork. In spare moments, he imagines chasing beams of light, riding waves of electricity, asking what the universe would look like from impossible perspectives. The equations he develops in those quiet hours will reshape our understanding of space, time, and gravity. Yet when astronomers begin suggesting the cosmos itself is expanding, Einstein resists the idea. He adds a term to his equations, the cosmological constant, to force the universe to remain static, eternal, balanced forever. Years later, facing mounting evidence, he will call this adjustment his greatest blunder. Meanwhile, in Belgium, Georges Lemaitre works alone on similar problems. Trained in physics and mathematics, ordained as a Catholic priest, he publishes careful papers proposing that the universe began as a single point and has been expanding ever since. Colleagues react with skepticism. Some dismiss the idea outright. A cosmos with a definite beginning feels too close to religious narrative, too uncomfortable for purely scientific taste. The observations, however, keep building. Edwin Hubble confirms that galaxies are receding in every direction, their light stretched redder the farther they lie. The pattern is uniform, no preferred center, no edge, just steady expansion everywhere we look. Running the film backward leads to the same conclusion: smaller yesterday, denser last century, hotter a million years ago. In 1949, astronomer Fred Hoyle appears on BBC Radio to defend his competing vision: a steady-state universe, infinite in time, continually creating matter to maintain perfect balance. Searching for a vivid way to ridicule the rival theory, he coins the phrase Big Bang, with clear mockery in his voice. The name catches on, despite, or perhaps because of, the original sarcasm. Many leading minds preferred an eternal cosmos, precisely because a true beginning carried implications they wished to avoid. It forced questions about causation, about boundaries, about what might lie beyond natural law. Einstein's constant was one attempt to escape the idea. Others proposed different modifications, different interpretations, all seeking to preserve a universe without a first moment. Then, in the spring of 1965, two radio astronomers in New Jersey encountered something they could not explain. Arno Penzias and Robert Wilson were calibrating a sensitive horn antenna at Bell Laboratories, preparing it for satellite communication work. No matter how thoroughly they tested, a faint, uniform hiss persisted in their readings. They checked every component. They climbed inside the giant dish to clear away pigeon nests and droppings. They recalibrated again and again. The noise remained, steady, coming from every direction, day and night, corresponding to a temperature just above absolute zero. By chance, a group at nearby Princeton University had been predicting exactly this kind of signal. Theorists there expected a faint microwave glow left over from a hot, dense early phase, a relic radiation that would have cooled as the universe expanded. When the two teams finally connected over the puzzling data, the realization arrived slowly, like light spreading across a darkened room. The hiss was real. It was ancient. It was the cosmic microwave background, the oldest light humanity had ever detected, stretched across billions of years into a whisper we could finally hear. News spread quickly through the scientific world. The discovery provided powerful support for the expanding universe model. The ancient question, how everything began, seemed, for the first time, to have a concrete answer rooted in observation rather than myth. A hot, dense state expanding into the cool vastness we see today. The afterglow still bathing us from every direction. For a moment, the picture felt complete. The primeval atom, the expansion, the relic light, all fitting together with elegant precision. The long human search appeared to reach its destination. Yet even in that moment of triumph, a faint uncertainty lingered at the edges. Evidence like everything else in the cosmos, has a way of hiding deeper mysteries. Every atom in your body was once squeezed into a point smaller than this period. So was every star, every galaxy, every possibility of life. Let the weight of that settle gently. Everything you have ever known, everything you love or fear, every thought that has ever passed through your mind, all of it originated in a single, inconceivably dense seed, smaller than the dot at the end of this sentence. The scale defies ordinary imagination. Not just immense distances outward, but unimaginable compression inward. A state where the usual rules of space and physics break down entirely. A moment when time itself had no clear place to start. If the universe truly had a definite first instant, certain implications become impossible to avoid. Time stretching backward only to a sharp boundary. A point where causation, as we understand it, reaches its limit. Something, whether random quantum event, underlying law, or intentional design, must explain the appearance of everything from nothing. Many of the sharpest scientific minds have felt this same quiet discomfort. Stephen Hawking spent decades exploring models where time becomes space-like near the beginning, making before meaningless, like asking what lies north of the North Pole. Yet he acknowledged the philosophical weight of the question. Alan Guth, whose inflation theory reshaped cosmology, has spoken openly about the challenge a true origin poses. Roger Penrose points to the extraordinarily low entropy, the remarkable order of the initial state, as one of the deepest unsolved puzzles in physics. The reasoning unfolds slowly but inevitably. Either causes extend backward infinitely, an endless chain that satisfies some but leaves others searching for a deeper foundation, or the chain terminates at something beyond the physical order we study. Our equations describe the expansion beautifully, starting a tiny fraction of a second after the presumed beginning. But the singularity itself remains hidden behind an impenetrable curtain. This is not about pushing any single conclusion. It is about recognizing the depth of the question itself. The same wonder that kept ancient storytellers awake beneath starlit skies now keeps modern theorists pacing in the quiet hours. We have replaced primordial seas and cosmic eggs with quantum fields and curved space-time. But the underlying unease persists unchanged. Your own existence rests delicately within this mystery. The hydrogen in your water, the calcium in your bones, the oxygen in your breath, all trace their lineage through stars that formed only because expansion proceeded at exactly the observed rate. Slightly faster, and matter would have dispersed too thinly for gravity to gather it into galaxies. Slightly slower, and everything would have recollapsed into a fiery crunch long before complexity could emerge. The balance appears astonishingly precise. We continue to probe deeper. Telescopes reach farther. Mathematics grows more sophisticated. Theories stretch toward unification. Each advance reveals new layers of beauty and new layers of question. The journey is far from over. So let us now examine the story we have been told, piece by beautiful piece. and see where it begins to strain under its own weight. Imagine discovering that the entire sky is glowing with the leftover heat of creation, and that two men found it by accident while trying to get rid of pigeon poop. The silence from the end of our last chapter still hangs in the air, a vast emptiness that begs to be filled. But listen closely now. Do you hear it? That faint hiss, like the static between radio stations on a long night drive? It's not imagined, it's real. We're tuning into the actual sound of the cosmic microwave background radiation, recorded and played softly beneath my words. This is the echo of the universe's infancy, a whisper that has traveled across eons to reach us here, in this moment. Picture this. It's 1964 in Holmdel, New Jersey. Two engineers, Arno Penzias and Robert Wilson, are hunched over a massive horn-shaped antenna, the kind that looks like a relic from a science fiction film. This beast of a machine, built by Bell Labs, was meant for satellite communications, bouncing signals off orbiting balloons high in the atmosphere. But something was wrong. No matter what they did, a persistent noise plagued their measurements, a low, steady hum that wouldn't go away. It was everywhere. In every direction they pointed the antenna. At first, they thought it was interference, maybe faulty equipment, or birds. Yes, pigeons had nested inside the horn, leaving droppings that coated the sensitive surfaces. So they climbed in, scrubbed it clean, evicted the feathered intruders. But the noise remained. They checked wires, recalibrated instruments, even replaced parts. Weeks turned into months of frustration. This wasn't just any noise. It was uniform, isotropic, coming from all corners of the sky with the same intensity. And its temperature, a chilly 3.5 Kelvin, just a hair above absolute zero, the point where all molecular motion ceases. They didn't know it yet, but they were listening to the universe's oldest soundtrack. Meanwhile, just 30 miles away at Princeton University, a team of theorists led by Robert Decker was hunting for exactly this signal. They had dusted off an old idea from the 1940s, proposed by George Gamow and his colleagues. If the universe began in a hot, dense state, a Big Bang, then as it expanded and cooled, the intense radiation from that primordial fire should still linger, stretched by the expansion into microwaves. It would be the afterglow of creation itself, filling the cosmos like the fading heat from a blacksmith's forge. Penzias and Wilson, unaware of this theoretical prediction, finally picked up the phone. They called Dicker. The conversation was brief, but electric. "Boys," Dicker reportedly said to his team after hanging up, "we've been scooped." The excitement rippled through the small community of physicists like a wave. Papers were published in 1965, and the discovery earned Penzias and Wilson the Nobel Prize in 1978. But beyond the accolades, this was a human story, a tale of serendipity, persistence, and the quiet thrill of uncovering something profound by accident. Now, let's make this intimate. That cosmic microwave background, or CMB, isn't some abstract graph on a scientist's chalkboard. It's the oldest light in the universe, photons that decoupled from matter about 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form. These photons have journeyed for 13.8 billion years, redshifted by the universe's expansion from blazing visible light to cool microwaves. If you tune your car radio between stations, that static you hear, about 1% of it is the CMB. It's everywhere, seeping into our world. Think of it like this. Imagine a massive furnace, glowing white-hot after forging the stars. As it cools over millennia, the glow fades to red, then infrared, until it's just a subtle warmth you feel with your hand. The CMB is that final whisper of heat from the universe's birth. Or picture a campfire at dawn. The flames have died, the embers cooled, but if you hover close, you can still sense the residual glow. That's the scale we're dealing with, but stretched across the entire sky. What makes this discovery revolutionary isn't just its existence, it's its perfection. The CMB is astonishingly uniform. Measure it in one patch of sky, then another a billion light years away. The temperature is the same, to within 1 part in 100,000. No natural process in our mature universe could achieve such smoothness. Galaxies clump, stars explode, gravity pulls matter into webs and voids. Yet this radiation is even, like a perfectly still pond at midnight. Pause here, and let that sink in. For the universe to be this uniform on such vast scales, something extraordinary must have occurred in its earliest instance. Faster than light could travel, ironing out every irregularity. Light, after all, has a speed limit, and in the time since the Big Bang, it couldn't have coordinated temperatures across the observable cosmos. This horizon problem hints at mechanisms beyond the standard Big Bang model, like cosmic inflation, a rapid expansion in the universe's first fraction of a second. But before we dive deeper, ground yourself in the present. Your body, right now, radiates heat at about 37 degrees Celsius, warm and alive. The CMB, it's cooled to just 2.7 Kelvin, a frigid testament to the universe's relentless expansion. It's a chilling reminder. We live in a cosmos that's been cooling for billions of years, from a fiery youth to this vast, dark maturity. And yet, in that cold echo, we hear the story of our origins. This perfect glow became the cornerstone of modern cosmology. Yet perfection, when examined too closely, often hides the deepest imperfections. In the universe's first 3 minutes, more precise chemistry happened than in all the stars that have burned since. And we carry the receipts in every breath we take. From the ancient light of the CMB, we now plunge into the fire itself, the scorching crucible of the universe's first moments. Imagine the clock ticking forward from the Big Bang, not billions of years, but mere seconds. The cosmos is a seething plasma, hotter than a billion suns, where particles smash together at speeds approaching light. Protons and neutrons, the building blocks of atoms, are born in this chaos, fusing in a frantic dance before the expansion cools everything too much for reactions to continue. This is Big Bang nucleosynthesis, or BBN, the cosmic alchemy that forged the lightest elements in the universe's opening act. Think of it as a hurried baker in a kitchen that's cooling by the second. You have just 3 minutes to mix your ingredients before the oven shuts off forever. No time for fancy pastries. Only the simplest recipes will do. Protons, hydrogen nuclei, dominate, but some collide with neutrons to form deuterium, a fragile isotope that's like the dough that barely holds together. From there, helium emerges, 2 protons and 2 neutrons, stable and abundant. A tiny sprinkle of lithium and beryllium follows, but nothing heavier. The window slams shut as the temperature drops below 1,000,000 degrees, freezing the ratios in place. The precision here is breathtaking. For every 10 billion hydrogen atoms, theory predicts about 25% helium by mass, exactly what we observe in the oldest stars and gas clouds. Deuterium clocks in at 1 part per 100,000 hydrogen atoms, a number so delicate that even slight changes in the early universe's conditions would erase it. Lithium, predicted at around 10 parts per billion. These aren't guesses. They're calculations rooted in particle physics, nuclear reaction rates, and the expansion rate of the universe. What makes BBN so compelling is its predictive power. George Gamow and his team sketched this out in the late 1940s, long before we had the tools to verify it. Decades later, with telescopes like Hubble peering into pristine pockets of the cosmos, gas clouds untouched by stellar forges, we measured these abundances. The match was stunning. Helium in ancient quasars, spot on. Deuterium in distant galaxies, within error bars. It's like finding a recipe from antiquity and baking it today, only to discover it tastes exactly as described. But here's where the narrative deepens. We breathe this evidence every day. The helium in your party balloons, mostly primordial, forged in those first minutes. The hydrogen in your water, straight from the Big Bang. Even the air in your lungs carries traces of this cosmic chemistry. It's a direct link, making the abstract feel personal. Yet no story is without its shadows. Lithium presents a puzzle. Observations consistently show about half the predicted amount, too low to dismiss as measurement error, too consistent to ignore. Is it a flaw in our understanding of early nuclear reactions? Or something more profound, like undiscovered particles influencing the fusion rates? The voice in our tail pauses here, letting the discrepancy linger like an unresolved chord in a symphony. This isn't a crack that topples the edifice. BBN remains a pillar of the Big Bang model. But it reminds us that science thrives on anomalies. They are the breadcrumbs leading to deeper truths. For now, we celebrate the triumph. In 3 minutes, the universe performed chemistry more exact than all the stellar furnaces that followed, seeding the cosmos with the elements that would build planets, life, and us. 2 great pillars held up the Big Bang, light from the first moments and elements forged in the fire. But even the strongest pillars can cast long shadows when the light is turned upon them. We have photographed the universe as a newborn, but the delivery room itself remains hidden in perfect darkness. With the CMB's glow and the light element's legacy as our foundation, let's weave in the broader tapestry. The evidence that paints the universe as a dynamic, evolving entity. Start with Edwin Hubble in the 1920s, gazing through the Hooker telescope on Mount Wilson. He noticed galaxies receding, their light stretched redward like a siren's wail, Doppler shifting as it flees. This redshift wasn't random. Farther galaxies moved faster, implying an expanding universe. It's as if we're raisins in a rising loaf of bread, each seeing others pull away proportionally. Fast forward. This expansion isn't static. Quasars, blazing beacons powered by supermassive black holes, dominate the distant early universe, but fade in number closer to home. Galaxies evolve too. Young ones are irregular, star-bursting whirlwinds. Older ones, like our Milky Way, are stately spirals, peer across cosmic time. And it's like rewinding a film. The farther you look, the denser, hotter, and more chaotic it gets. Radio waves from ancient hydrogen clouds, gamma rays from exploding stars, X-rays from hot gas in clusters, all align with this narrative. The universe was once compact, its contents squeezed into a volume smaller than we can fathom, then burst forth in expansion. Observations from satellites like COBE, WMAP, and Planck have mapped the CMB's tiny fluctuations, ripples that seeded galaxy formation. These aren't random. They match predictions from inflationary models, where quantum jitters were amplified into cosmic structure. Bask in this elegance for a moment. Every wavelength, every instrument tells the same story. A hot, dense past expanding into our cooler present. It's a symphony of consistency, human ingenuity capturing the cosmos's biography. But now, the reveal. All this evidence confirms the universe was hot and dense, expanding from that state. It describes the evolution brilliantly, the bang part. Yet it says nothing about a singularity, a true beginning at time zero. The CMB veils the first 380,000 years. Before that, the universe was opaque, light trapped in plasma. What preceded? Eternal inflation, a bounce from a previous contraction. Multiverses? We don't know. The big in Big Bang is a misnomer. It's not about the origin, but the aftermath. Let that silence settle. We've imaged the newborn universe, the Planck satellite's oval map of CMB ripples, like frozen waves on an ancient sea. But the delivery room, shrouded in darkness, beyond our reach. So the Big Bang describes the universe's early evolution brilliantly. Yet three puzzles, buried in the very success of the theory, began to whisper that the story was incomplete. Look left across the sky. Look right. These two patches of space have never spoken to each other. Yet, they are identical twins. How is that possible? We've lingered long enough in the triumph of the Big Bang's evidence. The ancient light, the primordial elements, the grand expansion. But every great theory casts shadows where the light doesn't quite reach. The first of these shadows fell across the cosmic microwave background itself, that perfect glow we celebrated in the last chapter. Stand with me for a moment and imagine the observable universe as a Bohr sphere centered on you. Light from the farthest edges has taken 13.8 billion years to reach us, so we're seeing those regions as they were long ago. Now picture two patches of sky directly opposite each other, one to the east, one to the west. These regions are separated by more than 27 billion light-years today. In the entire history of the universe, no signal, no particle, no influence traveling at the speed of light could ever have journeyed from one patch to the other. They lie outside each other's causal horizon, like two people born on opposite sides of a vast island who have never met, never communicated, never even heard of each other. Yet when we measure the temperature of the cosmic microwave background in those two directions, they match to within 1 part in 100,000. The same uniformity holds no matter which pair of opposite directions you choose. The entire sky is thermally equilibrated to an astonishing degree. Early cosmologists found this deeply unsettling. In the standard Big Bang picture, different regions of the early universe should have evolved independently if they were never in causal contact. Some should have been slightly hotter, others cooler, leading to blotches in the CMB we simply don't see. Instead, the background radiation looks as though the whole cosmos was once in perfect thermal equilibrium, carefully coordinated before expansion pulled everything apart. Think of it like this. Imagine arriving at a party where every guest, strangers to one another, is wearing exactly the same outfit, same color, same cut, even the same loose thread on the sleeve. You'd immediately suspect some prior arrangement, some hidden communication. The universe presents us with exactly that mystery, but on a scale so vast it defies intuition. Physicists drew light cones on blackboards, those diamond-shaped diagrams showing everything that can influence a point in space and time. For distant patches of the CMB, the cones don't overlap in the early universe. Information could not have passed between them. Yet the temperatures agree, as if they had been in contact, as if some mechanism synchronized them before the light cones grew apart. The numbers make the problem vertiginous. In the observable universe today, there are roughly 10 to 80 such causally disconnected regions that all share the same temperature to exquisite precision. How did they all know to start at exactly the same thermal state? The standard Big Bang model offers no answer. It simply assumes the initial conditions were like that, perfectly uniform across impossible distances. But assumptions like that begin to feel less like science and more like sweeping the mystery under the cosmic rug. This horizon problem, as it came to be called, was one of the first cracks in the otherwise beautiful facade. It whispered that something crucial was missing from our story of the universe's earliest moments. This was only the first shadow. A second waited in the very geometry of space itself. The universe is balanced on a knife edge so sharp that if it had tilted even slightly in its first second, everything we know would have collapsed or flown apart. From the puzzle of uniformity, we turn to an even subtler enigma, the shape of space itself. Most of us experience geometry locally. Here on Earth, the ground looks flat because we're tiny compared to the planet's gentle curve. On cosmic scales, space can curve too. It might be positively curved like the surface of a sphere, a closed universe. Negatively curved like a saddle, an open universe. Or perfectly flat, infinite, or with a special topology. Observations from the CMB, from galaxy surveys, from supernova distances, all converge on one conclusion. The universe is flat to within observational error, perhaps 1 part in 1,000 or better. That flatness is beautiful, but it's also profoundly strange. In an expanding universe, curvature behaves counterintuitively. If space starts with even slight positive curvature, expansion makes it curve more and more over time, eventually collapsing the cosmos in a big crunch. If it starts with slight negative curvature, expansion drives it toward ever greater openness, diluting matter until the universe becomes cold and empty far sooner than ours has. Only perfect flatness allows the long, slow evolution we actually observe, one that has lasted nearly 14 billion years and produced galaxies, stars, planets, and us. Here's the catch: flatness is unstable. Any tiny deviation from zero curvature grows exponentially with time. To be as flat as we see today, the universe at 1 second after the Big Bang had to be flat to 1 part in 1060, an almost inconceivable degree of fine-tuning. Picture a pencil balanced perfectly on its tip. In everyday life, the slightest breeze, the tiniest imperfection, sends it tumbling within moments. Now imagine that pencil remaining upright, not for seconds, but for billions of years. That's the level of balance required for cosmic flatness, without some stabilizing mechanism. Cosmologists call this the flatness problem. It's not that flatness is impossible, it's that it demands initial conditions tuned with precision far beyond anything else in physics. The electromagnetic force and the strong nuclear force are balanced to maybe 1 part in 1040 in some theories. Here we're talking 10^60. It feels less like a natural outcome and more like an engineered one. The discomfort is palpable in the literature. Steven Weinberg once wrote that the flatness problem makes the universe seem extremely contrived. Others described the necessary initial conditions as improbable to the point of absurdity. The standard Big Bang model again has no explanation. It simply postulates that the universe began with this knife-edge balance already in place. The flatness problem compounds the horizon problem. Both suggest the early universe was set up with extraordinary care, uniform beyond causal reach, and geometrically balanced to fantastical precision. 2 separate coincidences, each unlikely on its own, begin to look like symptoms of the same deeper issue. And there was a third shadow, one that should have left scars across the sky, but didn't. Physics predicted we should be drowning in particles that have never been seen, particles so massive they could bend starlight with their gravity alone. The final shadow comes not from what we see, but from what we emphatically do not see. In the 1970s, physicists developed grand unified theories, GUUTs, that promised to merge the strong, weak, and electromagnetic forces at extremely high energies. Energies naturally present in the very early universe. These theories were elegant and predictive, but they carried an awkward consequence. At the moment the forces separated, around 10 sols to 35 seconds after the Big Bang, topological defects called magnetic monopoles should have formed in huge numbers. A magnetic monopole is a particle with a single north or south magnetic pole, no opposite pole attached. Ordinary magnets always have both. Cut one in half, you get two smaller magnets, each with north and south. Monopoles would violate that rule. Theory predicted they'd be extraordinarily massive, about 10^16 times heavier than a proton, and produced copiously in the Gotti phase transition. The problem? Not one has ever been found. Despite dedicated searches with particle detectors, astrophysical observations, and even samples of lunar soil, the sky is clean of monopoles. Why is their absence troubling? Because in the standard Big Bang, once produced, these particles would be nearly impossible to destroy or dilute. They're stable, and expansion merely spreads them out. Calculations showed we should expect roughly one monopole per Hubble volume, meaning one within the entire observable universe today. But some models predicted far more, densities so high that their collective mass would dominate the cosmos, curving space-time noticeably and overclosing the universe long ago. Imagine particles so heavy that a single one outweighs entire galaxy clusters in gravitational influence, scattered throughout space like cosmic landmines. We should see their effects: distorted gravitational lensing, anomalous magnetic fields, tracks in detectors. Instead, the upper limit on their density is something like 1 per 10 20 Hubble volumes or lower. They are spectacularly missing. This monopole problem strikes at the heart of theoretical physics. Either the beautiful Gottis are wrong, possible, but many of their other predictions have held up, or something in the early universe dramatically reduced monopole density, diluting them by many orders of magnitude. Taken together, the three problems, horizon, flatness, and monopoles, form a triad of crises. Each arises from the standard hot Big Bang model's inability to explain why the universe looks the way it does without invoking extraordinarily special initial conditions. Uniformity without causal contact, flatness without fine-tuned balance, emptiness where theory demands abundance. These aren't minor inconsistencies. They challenge the very foundation of assuming the universe simply began in a singular state with no further mechanism. By the late 1970s, a growing number of cosmologists felt the theory was incomplete, that something dramatic must have happened in the universe's infancy to smooth it, flatten it, and cleanse it of unwanted relics. Three separate puzzles, one common thread. The universe's earliest moments needed something dramatic to smooth, flatten, and cleanse it. In 1980, a young physicist named Alan Guth proposed exactly that. In less time than it takes to blink, the entire observable universe grew from smaller than a proton to larger than a grapefruit. and everything we see today was born in that instant. The shadows we traced in the last chapter, the horizon problem, the flatness problem, the missing monopoles, hung over cosmology like unresolved questions in a detective story. By the late 1970s, physicists knew the standard Big Bang model was incomplete. It described the universe's evolution with stunning accuracy, but only by assuming initial conditions that seemed impossibly contrived. Something was missing, some hidden chapter before the hot, dense phase we could observe. Enter Alan Guth, a young postdoctoral researcher at Cornell University. It's December 1979. Guth is sleepless, pacing his apartment, scribbling equations on scrap paper late into the night. He's been wrestling with the monopole problem, trying to understand why grand unified theories predict relics we never see. Then, in a quiet eureka moment, he realizes something extraordinary. A phase transition in the very early universe could release energy in a way that doesn't just expand matter and radiation. It causes space itself to double, and double again exponentially. This is cosmic inflation, a brief but violent episode of super-rapid expansion, driven by the vacuum energy of a scalar field. Imagine water freezing into ice. As it solidifies, it releases latent heat, but the volume changes slowly. Now picture a false vacuum, a metastable state with high energy density that decays into the true vacuum we live in today. During that decay, the energy stored in the vacuum doesn't heat things up. Instead, it acts like a repulsive gravity, pushing space apart at an accelerating rate. The mathematics is elegant. In the standard Big Bang, expansion slows over time due to gravity. During inflation, it accelerates. The scale factor grows exponentially. Yet, where Q is time. In as little as 1032 seconds, a fraction so tiny it defies comprehension, a region smaller than an atom could expand by a factor of 1026 or more. That's enough to take a patch tinier than a proton and blow it up to the size of a grapefruit or larger. But the real magic lies in what this does to the problems plaguing the Big Bang. First, the horizon problem vanishes. Before inflation, our entire observable universe was crammed into a causally connected region, smaller than a grain of sand. Thermal equilibrium had time to establish itself uniformly. Then inflation stretched that tiny coordinated patch into the vast cosmos we see, carrying the uniformity with it. Those opposite patches of sky that seem never to have communicated. They were once close neighbors, exchanging heat and information freely. Second, the flatness problem resolves naturally. Exponential expansion is like blowing up a balloon. No matter how curved the surface was initially, stretching it enormously makes any local region appear flatter and flatter. A crumpled piece of paper, inflated to the size of the Earth, would look smooth as glass. Inflation drives the curvature parameter toward zero with overwhelming force, explaining why the universe is flat today without needing knife-edge initial conditions. Third, the monopoles and any other unwanted relics are diluted beyond detection. produced before or during inflation, they're spread across a volume so immense that fewer than one ends up in our entire observable universe. The sky is clean, not because monopoles don't exist, but because inflation pushed them far beyond our horizon. Guth's insight, published in 1981, was breathtaking in its simplicity. One mechanism, one brief epoch, solved three unrelated crises at once. It wasn't patching holes, it was rewriting the opening act of cosmic history. And it did so with a prediction. Those quantum fluctuations in the tiny pre-inflationary patch, stretched to macroscopic scales, would leave faint imprints in the cosmic microwave background. Temperature variations of about 1 part in 100,000, with a specific statistical pattern. Inflation swept the problems under the cosmic rug with breathtaking simplicity. Yet the closer physicists looked at the mechanism itself, the more unsettling it became. The field that saved the Big Bang needed even more delicate initial conditions than the problems it solved. With the three shadows dispelled, inflation quickly became the new cornerstone of cosmology. But what exactly powered this explosive growth? At its heart lies the inflaton, a hypothetical scalar field permeating space, much like the Higgs field discovered decades later. The key isn't the field itself, but its potential energy landscape. Picture a ball rolling across a hilly terrain. In most field theories, the potential has a minimum where the field settles, releasing energy as particles or heat. For inflation, the potential needs a long, almost flat plateau, a gentle slope where the ball rolls slowly, barely accelerating. While it lingers on that plateau, the vacuum energy remains nearly constant, driving exponential expansion. Only when the ball finally reaches the steeper drop to the minimum does inflation end, the energy reheating the universe into the hot Big Bang we know. This slow roll phase is crucial. It must last long enough, at least 60 E-folds of expansion, to solve the horizon and flatness problems. The plateau must be extraordinarily flat, tuned to better than 1 part in 10^10 or more in many models. Too steep, and inflation ends too soon. Too bumpy, and the expansion becomes chaotic. Yet the payoff is profound. Quantum mechanics ensures that even in the smoothest vacuum, tiny fluctuations occur, random jitter in the inflaton field's value. During inflation, these microscopic ripples are stretched across vast distances, freezing into classical perturbations as they exit the horizon. When inflation ends, they re-enter as density variations, slightly over-dense regions that gravity amplifies into galaxies, clusters, and the cosmic web. These same fluctuations imprint on the cosmic microwave background. The temperature map we see today, the famous oval from Planck, is a snapshot of those stretched quantum seeds. Inflation predicts a nearly scale-invariant spectrum, fluctuations of roughly equal strength on all scales, with a slight tilt toward larger scales being weaker. It also predicts Gaussian statistics, acoustic peaks from sound waves in the primordial plasma, and a specific pattern of polarization. The vindication came swiftly. In 1992, the COBE satellite detected temperature variations exactly at the predicted level. 1 part in 100,000. Later missions, WMAP in 2003, Planck in 2013, refined the measurements, confirming the spectrum, the peaks, the flatness, even subtle effects like gravitational lensing of the CMB by intervening matter. Inflation's predictions matched reality with a precision that rivals the finest theories in physics. For a moment, cosmologists could breathe easy. The Big Bang, augmented by inflation, seemed complete. A seamless story from a quantum seed to the stars. But scrutiny revealed a shadow within the solution itself. The inflaton potential's flatness requires fine-tuning rivaling or exceeding the flatness problem inflation solved. Why is the plateau so unnaturally smooth? In particle physics, quantum corrections typically introduce large slopes or bumps unless parameters are adjusted with exquisite care. Moreover, the field must start near the plateau with very low kinetic energy, another special initial condition. Some models mitigate this with symmetries or dynamics, but many require tuning comparable to 1 part in 10,050 or worse. Inflation explains why the universe appears fine-tuned by making most initial conditions lead to flat, uniform outcomes. Yet the inflaton itself seems to demand the very contrived setup inflation was meant to avoid. The rescue came at a cost, trading one set of special conditions for another, perhaps more hidden. But one feature of inflation would prove far more radical than anyone first imagined. Inflation doesn't just happen once, it never stops. And every time you think it has ended, it begins again somewhere else, forever. Inflation's most profound implication emerged not from its beginning, but from its end, or rather, the difficulty of ending it gracefully everywhere at once. In the slow roll picture, the inflaton field rolls down its potential, eventually oscillating around the minimum and decaying into particles, reheating the universe into a hot, radiation-dominated phase. Our Big Bang begins there, inside one region where inflation has stopped. But quantum fluctuations complicate this. Even as the field rolls toward the minimum in some places, random quantum kicks can push it back up the hill in others. In those regions, the high vacuum energy persists, and exponential expansion continues unabated. The result is eternal inflation. Once started, inflation never fully ends on large scales. Regions where the field has rolled down form bubble universes like ours. Pockets where reheating occurs, expansion slows, and matter condenses into stars and galaxies. But these bubbles are surrounded by space that keeps inflating eternally, perpetually spawning new bubbles through quantum tunneling or fluctuations. Picture foam bubbling in a glass. Each bubble is a universe, expanding internally while the surrounding false vacuum grows faster than light, isolating the bubbles forever. Our observable universe is just the interior of one such bubble, a tiny fraction of a much vaster, eternally inflating whole. This multiverse isn't optional in most inflationary models. It's inevitable. Different bubbles can nucleate into different vacuum states, distinct minima in a complex potential landscape predicted by string theory or quantum gravity. Each vacuum has its own physical constants: strength of gravity, mass of the electron, number of dimensions that expand. Most bubbles are sterile, too short-lived, too empty, or with laws hostile to chemistry and life. A few, like ours, permit stable atoms, long-lived stars, and the complexity needed for observers. The implications cascade. We no longer live in the universe, but in a universe, one among infinitely many. The large-scale structure we see, the ripples in the CMB, are local features shaped by our bubble's particular reheating and constants. Guth himself, along with collaborators like Andre Linde and Alex Valenkin, developed these ideas in the 1980s. Eternal inflation transformed a technical solution into a philosophical upheaval. It explained why our patch looks the way it does, not because the initial conditions were uniquely tuned, but because inflation produces every possible patch somewhere, and we can only observe one suitable for our existence. Yet this raises a question that cuts deeper than any before. In a multiverse, where every conceivable set of laws is realized infinitely often, why does our bubble have constants that allow galaxies to form slowly enough for life to evolve? Why is the cosmological constant tiny but positive, permitting a vast, accelerating future? Why do the forces balance just right for heavy elements, planets, biology? The answer inflation suggests is anthropic. We find ourselves in a rare, life-friendly bubble because only those permit minds to wonder about the question. In hostile bubbles, no observers arise to ask. This endless bubbling raised a question no one wanted to ask. If there are infinite universes with every possible law, why do ours permit stars, planets, and minds to wonder about it all? The laws of physics might not be fundamental truths, but random rolls of dice in an infinite cosmic casino. The eternal inflation we uncovered in the last chapter didn't just expand our view of the cosmos. It shattered it into infinitely many pieces. What began as an elegant fix for the Big Bang's problems had spiraled into something far grander and far more unsettling. A multiverse where our universe is just one bubble among countless others, each potentially governed by different laws. To understand how we arrived here, we must venture into the string theory landscape, a vast theoretical terrain that emerged in the 1990s and 2000s. String theory, the leading candidate for unifying quantum mechanics and gravity, posits that fundamental particles are tiny vibrating strings in higher dimensions. To make this consistent with our four-dimensional world, the extra dimensions must curl up into compact shapes like intricate origami. Here's the revelation. There isn't one unique way to fold those dimensions. There are many, perhaps 10, 500 or more distinct configurations, each corresponding to a different vacuum state. Each vacuum has its own set of physical constants: the strength of gravity, the masses of particles, the number of forces, even the value of the cosmological constant. It's as if the universe's rulebook isn't a single elegant volume, but an immense library where every possible book exists, each with slightly or wildly different laws of physics. Most of these vacua are barren. In some, gravity is too strong. crushing atoms before they form. In others, the electromagnetic force repels protons, preventing nuclei from holding together. Many have cosmological constants so large that space expands too violently for galaxies to coalesce, or so negative that the universe collapses instantly. Only a vanishingly small fraction, perhaps 1 in 10, 100 or fewer, permit the gentle conditions needed for stars to burn steadily, planets to orbit, chemistry to unfold, and life to emerge. Eternal inflation populates this landscape. As the false vacuum expands forever, quantum tunneling events nucleate bubbles into every possible vacuum. The process is endless, producing infinitely many universes of each type. In this cosmic lottery, every conceivable set of constants is realized somewhere, infinitely often. This brings us to the anthropic principle, an idea once dismissed by many physicists as philosophical hand-waving. It states simply, we observe the constants we do because only those allow observers like us to exist. In a multiverse, the fine-tuning puzzle dissolves, not because our universe is special, but because we could only ever find ourselves in one of the rare life-friendly ones. It's selection bias on a cosmic scale. Remarkably, some of the fiercest critics of anthropic reasoning began to change their minds. Leonard Susskind, a pioneer of string theory, once sought unique predictions from the theory. By the mid-2000s, confronted with the landscape's vastness, he argued that anthropic selection in a multiverse was inevitable. Steven Weinberg, who in 1987 used anthropic reasoning to predict a small positive cosmological constant years before its discovery, saw it vindicated. Even Andre Linde, co-architect of inflation, embraced the multiverse as the natural outcome of his models. For many, this shift felt like a betrayal of physics' traditional quest for fundamental, elegant laws. Instead of discovering why the constants are what they are, we explain them by saying, in most universes, no one is around to ask the question. The laws aren't necessary truths derived from first principles. They're environmental accidents, random outcomes in an infinite ensemble. Some find this liberating, freeing physics from the demand for uniqueness, allowing probability to take center stage. Others mourn the loss of certainty, sensing that science has traded deep explanation for statistical shrug. Yet the multiverse solution came with a price. It might be untestable, unfalsifiable, beyond the reach of science itself. In an infinite multiverse, everything that can happen does happen, an infinite number of times. So why do you exist in this version, reading these words, right now? The multiverse offers an anthropic explanation for fine-tuning, but infinity introduces a serpent into the garden, the measure problem. In a finite collection of universes, we could count how many have each set of constants and compute probabilities straightforwardly. But eternal inflation produces infinitely many bubbles of every type. Infinity divided by infinity is undefined. Every outcome, no matter how improbable, occurs infinitely often. How then do we assign probabilities? Which measure should we use to say our universe is typical rather than outrageously rare. Physicists have proposed various measures, counting bubbles by volume, by nucleation rate, by the number of observers they produce. But none agree. Some measures predict we should live in a universe with far more stars or different constants. Others lead to absurd conclusions, like expecting to be Boltzmann brains, fleeting consciousnesses in empty space, rather than evolved beings. Consider a simple paradox. Suppose most life-friendly universes have slightly different electron masses, making biochemistry richer or simpler. Why do we find ourselves in this one, with its particular balance? Or zoom in. In the multiverse, there are infinitely many exact copies of you, identical down to every atom, reading these words right now. There are also infinitely many where the text differs by one letter or where you stopped reading earlier. How do we define you across this infinite duplication? Why does your experience align with this specific version? These questions aren't mere philosophy. They strike at prediction. Inflation once promised testable forecasts for the CMB. The multiverse threatens to render cosmology post-dictive, explaining anything after the fact via anthropic selection. If every outcome happens somewhere, no observation can falsify the theory. Leading researchers have voiced deep unease. Paul Steinhardt called the measure problem fatal, arguing it turns inflation into pseudoscience. David Gross worried it abandons the search for unique laws. Even proponents like Guth and Linda admit the problem remains unsolved, with some suggesting it may be inherently unresolvable, requiring a theory of quantum gravity we don't yet possess. The vertigo is profound. We set out to explain why the universe is uniform, flat, and life-friendly. Inflation solved the first two elegantly, but the price was a multiverse where fine-tuning is explained by sheer numbers. Yet without a proper measure, we can't even say why we observe the constants we do. The theory risks becoming a beautiful story that explains everything, and therefore nothing. Some physicists refused to accept the multiverse. They searched instead for ways the universe could have begun without a singular, inexplicable start. Perhaps the universe didn't begin at all. It simply faded into existence like a wave on a shore that has no beginning. Not everyone was willing to trade elegance for infinity. In the 1980s and 1990s, a parallel strand of research sought to apply quantum mechanics directly to the entire universe, hoping to eliminate the singularity altogether. Stephen Hawking and James Hartle proposed the no-boundary proposal in 1983. In classical general relativity, time begins at the Big Bang singularity, a point where densities and curvatures become infinite and physics breaks down. But quantum gravity blurs sharp edges. Hawking suggested treating time as imaginary near the beginning, like latitude near the South Pole. Picture the universe's history not as a cone with a sharp tip, but as a smooth sphere. Space expands from a finite minimum like the Earth's surface, curving from the pole. There is no boundary, no singular start, just a gentle transition from a quantum regime where time loses its ordinary meaning. The wave function of the universe, solved via path integrals, assigns probabilities to different histories, favoring smooth, inflationary ones. Alexander Vilenkin offered a complementary picture: quantum tunneling from nothing. In quantum field theory, particles pop in and out of empty space. Vilenkin imagined the universe itself tunneling from a state of literal nothingness, no space, no time, into a small, closed geometry that then inflates. Its creation ex nihilo, but governed by physical law rather than divine fiat. Both approaches aim to make the universe self-contained, requiring no external cause or special initial conditions. The singularity dissolves into quantum fuzz. The universe emerges probabilistically, like radioactive decay. These ideas are mathematically beautiful, evoking a cosmos that simply is, eternal in a timeless sense. Yet scrutiny reveals familiar echoes. Many no-boundary or tunneling solutions naturally incorporate inflation to match observations. And once inflation begins, eternal reproduction often follows, bubbles budding forever, leading back to the multiverse. Critics note that selecting the right wave function or tunneling potential still involves choices that feel anthropic. Why this quantum cosmology rather than another? The promise of uniqueness slips away. Other researchers took a different path entirely, rejecting the singularity and imagining the universe reborn from the ashes of a previous collapse. What if the Big Bang was not the beginning, but merely the latest rebirth in an endless cycle of death and renewal? The multiverse left us contemplating infinity, an endless froth of bubbles, each with its own laws, our existence a mere anthropic accident. Quantum cosmologies tried to smooth away the singularity, only to loop back into eternal reproduction. Many physicists felt uneasy, sensing that the origin question had slipped further from reach. What if there was no true beginning at all? What if the universe has simply always been, pulsing through eternal cycles of expansion and contraction? Picture this: a cosmos that swells to vast size, cools, then gravity pulls everything back into a fiery crunch. Matter compresses to unimaginable density, temperatures soar, and then, somehow, it rebounds. A new expansion begins, fresh and hot, like a phoenix rising from its own ashes. No singular start, no need for a first cause, just an endless rhythm, death giving way to rebirth forever. Early hints of this idea appeared nearly a century ago. Alexander Friedmann, whose equations first revealed expanding universes in 1922, also considered oscillating solutions, worlds that expand, recollapse, and expand again. Richard Tolman explored these cyclic models in the 1930s, imagining thermodynamic cycles where entropy builds but perhaps resets. Yet classical general relativity doomed them. Each crunch ends in a singularity, a point of infinite density where physics fails. The bounce could never happen smoothly. The universe would simply end. Modern hope comes from quantum gravity. In loop quantum gravity, a leading approach to unifying quantum mechanics and relativity. Space-time is woven from tiny, discrete loops. At the Planck scale, where densities approach 10⁻93 grams per cubic centimeter, these loops resist further collapse. Repulsive quantum forces emerge, turning the big crunch into a big bounce. The singularity evaporates, replaced by a smooth transition. Researchers like Martin Borgewald and Abhay Ashtekar have simulated this in simplified models. As the universe contracts, volume approaches zero, but never reaches it. A minimum size sets the turnaround. Time continues through the bounce. The pre-bounce era is a mirror of our expanding phase, contracting from a previous Big Bang. Entropy and matter carry forward, but the quantum regime scrambles or resets certain features. These bouncing cosmologies offer an eternal universe without beginning or end. No need for inflation's explosive start. The bounce itself can generate the density perturbations that seed galaxies. Some models even produce a nearly scale-invariant spectrum matching CMB observations. For those weary of multiverses and fine-tuning, the bounce feels like a return to simplicity. One universe, self-sustaining, cyclic. Yet every bounce must carry information forward. And entropy poses a relentless challenge. Across the infinitely stretched future of one dying universe, the echoes of ancient black holes might appear as faint circles in our microwave sky. The promise of a bounce is elegant, but one obstacle looms large, the second law of thermodynamics. Entropy, disorder, always increases. In a cyclic universe, each expansion dilutes matter. Stars burn out, black holes evaporate via Hawking radiation, leaving a cold, diffuse soup. When contraction begins, gravity concentrates energy. But entropy should keep rising. Over cycles, disorder accumulates relentlessly. How then does each new expansion begin with the low entropy needed for structure formation, smooth plasma ready to clump into galaxies? Without a reset, the universe would grow ever more disordered, cycles becoming shorter and messier until meaningful structure ceases. Tolman recognized this in the 1930s. His oscillating models suffered irreversible entropy buildup. Roger Penrose, undeterred, proposed a radical solution in 2005, conformal cyclic cosmology, or CCC. The key insight is conformal invariance, physics that preserves angles but rescales distances. In the distant future, a universe dominated by a positive cosmological constant expands forever. Matter dilutes to nothing. Only radiation and evaporating black holes remain. As the last black holes fade, the universe becomes empty, filled with massless photons. Here's the trick. Without mass, clocks lose meaning. Distances become irrelevant. The infinitely large cold end conforms to a smooth, finite geometry. Penrose rescales this conformal boundary, gluing it seamlessly to the Big Bang of the next eon. The diluted radiation of one era's end becomes the dense, hot plasma of the next's beginning. Entropy resets not by magic, but because the rescaling erases the distinction between big and small. Information from the previous aeon carries forward subtly. Black hole mergers in one cycle produce gravitational waves that, after conformal rescaling, imprint as low-frequency ripples in the next eon's CMB. Penrose and collaborators searched for these signatures, concentric circles of temperature variation, or Hawking points, echoes of supermassive black hole evaporations. Claims of detection in Planck data sparked debate. Some analyses found anomalous rings aligned with known black hole candidates in our aeon. Others argued coincidence or foreground contamination. The evidence remains tentative, but the idea captivates. Our CMB might bear scars from a previous universe's cataclysms. CCC avoids singularities entirely. No bounce needed, just infinite eons linked conformally. It's a universe that forgets its own death, reborn smooth and ordered each time. Other ideas went further, challenging general relativity itself at the largest scales. Imagine our universe born not from a point, but from the gentle collision of vast higher dimensional membranes drifting through the bulk. While loop quantum bounces and conformal cycles offered eternal alternatives, another class of models drew inspiration from string theory's higher dimensions. In the late 1990s, the ekpyrotic scenario emerged, a cyclic universe born not from crunch and bounce, but from the collision of brains. String theory posits our four-dimensional space-time as a brain, a membrane embedded in a higher dimensional bulk. In the ekpyrotic model, proposed by Paul Steinhardt and Neil Turok, two parallel brains drift toward each other through the bulk, attracted by a gentle potential. When they collide, kinetic energy converts to heat and matter, igniting a hot expanding phase on our brain. The Big Bang. The collision is slow and grazing, not violent. Space on the brain expands rapidly during the impact, mimicking inflation's effects without an inflaton field. Quantum fluctuations on the approaching brains stretch into density perturbations, seeding galaxies with the observed nearly scale-invariant spectrum. After expansion, radiation and matter dilute, the brains separate. Then the potential pulls them back for another collision. Cycles repeat eternally, each bang a brain crash. Entropy increases per cycle, but a small dilution mechanism, perhaps extra-dimensional leakage, prevent runaway buildup. The cyclic ekpyrotic model, refined in the 2000s, produces CMB features like acoustic peaks and slight scale tilt without invoking exponential inflation. It avoids the multiverse. Each cycle is within one universe, governed by consistent higher dimensional laws. Critics note challenges, matching precise CMB polarization, handling dark energy, ensuring smooth collisions. Yet the appeal is strong. An alternative generating observed fluctuations from classical dynamics in extra dimensions, sidestepping inflation's fine-tuning and eternal bubbling. These models, loop bounces, conformal eons, brain collisions, represent serious contenders. They share a vision, an eternal cosmos, where the Big Bang is not origin but transition. No singularity, no multiverse lottery, no untestable infinities. Just a universe that endures, cycling or rebounding through mechanisms rooted in quantum gravity or string theory. While theorists debated eternal cycles and colliding brains, a new telescope began to peer deeper into the past than ever before. And what it saw threatened every story we had told. A telescope the size of a tennis court, chilled to near absolute zero, began to show us the universe's infancy, and the baby already looked middle-aged. For decades, cosmologists had peered into the cosmic dawn with ground-based telescopes and Hubble, catching only faint glimmers of the universe's first chapters. The epoch of Rayonization, when the first stars ignited, flooding the neutral hydrogen fog with ultraviolet light, remained shrouded. Models predicted a gradual awakening, tiny proto-galaxies coalescing slowly, merging over billions of years into the grand structures we see today. The very first stars, population 3, were expected to be massive, but isolated, lighting up perhaps 200 to 400 million years after the Big Bang. Then came Christmas Day, 2021. Atop an Ariane 5 rocket from French Guiana, the James Webb Space Telescope unfolded its golden wings and began its million-mile journey to Lagrange Point 2. This was no ordinary instrument. Its 6.5-meter segmented mirror, plated with gold for infrared sensitivity, dwarfed Hubble's. Sun shields the size of a tennis court deployed to keep the observatory at a frigid -225 degrees Celsius, shielding delicate detectors from heat. JWST was built to see farther back in time than ever before, into the infrared, where light from the earliest galaxies has been stretched by expansion. The early months were nail-biting. Engineers aligned the 18 hexagonal segments with nanometer precision, turning a blurred mess into images sharper than predicted. The first test field, SMACS 2-3, released in July 2022, stunned the world. A deep field vista teeming with gravitational lenses, arcs of ancient light bent by foreground clusters. But the real revelations came with the science programs, SEERS, GLASS, NG-Deep, probing redshifts beyond 10, when the universe was less than 500 million years old. What JWST saw defied expectations. Galaxies already existed in abundance at redshift 13 or higher, only 300 million years post-Big Bang. These weren't fragile seedlings. Many were massive, with stellar populations rivaling modern spirals. Bright, compact cores suggested organized disks and bulges, chemical enrichment from multiple generations of stars. In standard models, such maturity required billions of years of hierarchical merging. Here, the universe seemed to have skipped childhood entirely. Astronomers spoke of impossible early galaxies. Papers poured out, confirming candidates like Jade's GS Z13-0, glimpsed just 320 million years after the beginning. The light had traveled 13.4 billion years to reach us. Yet these systems shone with the luminosity of hundreds of billions of stars. How had gravity assembled them so swiftly in a younger, denser cosmos? The excitement was palpable. Teams raced to analyze spectra, confirming distances via Lyman alpha dropouts. JWST wasn't just fulfilling promises, it was rewriting the timeline of cosmic structure formation. These unexpectedly mature galaxies were only the beginning of the surprises. Black holes 1 billion times the Sun's mass should take billions of years to grow. Yet JWST found them lounging in the cosmic nursery. The early galaxies were shocking enough, but JWST's infrared gaze pierced deeper, revealing processes that strained theory to its limits. Consider reionization, the era when ultraviolet light from the first stars and quasars ionized the intergalactic medium, clearing the fog. Models predicted a protracted struggle, ending around 1 billion years after the Big Bang. Yet JWST spectra showed strong Lyman alpha emission from galaxies at redshift 8 to 10, light that should have been absorbed by neutral hydrogen if reionization was incomplete. These bright lines suggested the process finished earlier, perhaps driven by unusually efficient star formation or unexpected energy sources. Then came the black holes, supermassive ones, anchoring modern galaxy centers, grow via accretion and mergers over cosmic time. Seeding them requires either rapid direct collapse of gas clouds or heavy seeds from the first stars. Standard theory capped early growth. 1 billion solar mass black hole at redshift 7, about 700 million years old, was already pushing limits, as seen in quasars like ULAS J1000 plus 0641. JWST shattered that ceiling. In surveys like SEERS and JADES, active galactic nuclei glowed fiercely in tiny host galaxies at redshifts 9 to 11. One candidate, in GNZ11, already known but re-observed, hinted at an overmassive black hole relative to its stars. Others, like UHD1 at redshift 10.1, hosted behemoths exceeding 1 billion solar masses when the universe was merely 4 million years old. Spectra confirmed broad emission lines and X-ray counterparts from Chandra, ruling out lensing illusions in many cases. Researchers expressed outright astonishment. "These black holes are too big, too early," became a refrain. Accretion at the Eddington limit, the maximum sustainable rate, would take hundreds of millions of years to build such masses from stellar remnants. Super Eddington growth? Possible, but rare and unstable. Direct collapse from pristine gas clouds could seed heavier starters, but required exquisitely tuned conditions. No fragmentation, suppressed star formation, intense radiation baths. The implications rippled. If black holes grew so voraciously, feedback might heat gas, stifling further formation, yet galaxies around them brimmed with stars. Oxygen and heavier elements appeared in abundance, implying multiple supernova generations in short order. Population 3 stars, metal-free giants, should dominate early light. Instead, spectra showed enriched chemistry. Conferences buzzed with crisis talks. Was star formation efficiency far higher in the early universe? Did dark matter play unexpected roles? Or were the redshifts mismeasured? Unlikely, given multiple confirmations. The scramble to revise models began. Enhanced seeding, prolonged accretion bursts, primordial black holes as dark matter candidates. JWST wasn't debunking the Big Bang. It was accelerating the dawn, compressing billions of years of evolution into mere hundreds of millions. Some began to whisper that the very expansion rate itself might be wrong. The universe appears to be expanding faster now than it should, as if the ruler we used to measure the early cosmos was subtly different from today's. Amid the upheaval from early galaxies and precocious black holes, JWST turned its precise instruments to a long-standing tension: the Hubble constant, HO, the current expansion rate. For years, two camps had clashed. Measurements from the early universe, via the cosmic microwave background and baryon acoustic oscillations, as mapped by Planck, predicted HO around 67 to 68 kilometers per second per megaparsec. Local measurements using Cepheid variables and type Ia supernovae calibrated by Hubble yielded higher values near 73 to 74. The discrepancy, dubbed the Hubble tension, exceeded 5 sigma, statistically improbable if the standard lambda CDM model held perfectly. JWST, with its superior resolution, promised to arbitrate. It resolved Cepheids in distant hosts without crowding errors that plagued Hubble, and observed tip-of-the-red giant branch stars as independent calibrators. Results from the first years, led by teams like Adam Ries's SH0AS project, confirmed the higher local value with unprecedented precision, around 73 km/s MPC. Multiple rungs of the distance ladder aligned: supernovae, surface brightness fluctuations, even gravitational waves from mergers. JWST's deep fields provided more hosts at cosmological distances, tightening the chain. Meanwhile, early universe probes, CMB from Planck, updated by Atacama Cosmology Telescope and South Pole Telescope, held firm at the lower value. The crisis deepened. If HO truly differed between epochs, the expansion history wasn't smooth. Perhaps dark energy evolved, or new physics intervened in the late universe. Early galaxies' maturity exacerbated this. Faster structure formation might correlate with accelerated expansion. Some proposed systematic errors, but independent methods converged on the higher rate. The tension wasn't resolving. It was solidifying into one of cosmology's deepest puzzles, with observations challenging every pillar, from galaxy formation timelines to reionization, black hole growth, and now the fundamental expansion rate. Physicists returned to the deepest question: what is space, time, and gravity at the ultimate scales? At the smallest scales, reality might be woven from tiny vibrating loops of pure energy, humming in 10 dimensions we cannot see. The James Webb Space Telescope has thrust us back to the cosmic dawn, revealing galaxies and black holes that matured far too quickly, an expansion rate that refuses to reconcile. Puzzles that gnaw at the foundations of our standard model. These tensions whisper the same message: to understand the universe's earliest moments, the true origin beyond the veil of the CMB, we must confront the irreconcilable clash between quantum mechanics and general relativity. Gravity, as Einstein described it, is the smooth curvature of space-time, a geometric dance on vast scales. Quantum theory, governing particles and forces, is a probabilistic storm of uncertainties and discreteness. At the Planck scale, 10⁻⁵ meters, where densities reach extremes, the two languages collide. Black hole horizons spawn paradoxes. The Big Bang singularity becomes a point where equations scream nonsense. To resolve the beginning, we need quantum gravity, a theory that marries the two pillars. String theory emerged in the 1970s as the boldest attempt. Forget point particles. Imagine fundamental reality as tiny one-dimensional strings vibrating in a higher dimensional space. Each mode of vibration corresponds to a different particle: electron, photon, graviton. The theory naturally includes gravity. Closed strings produce the massless spin-2 particle that mediates it. No infinities plague the calculations. String interactions smooth out ultraviolet divergences. To work consistently, string theory demands 10 dimensions. Our familiar 4, plus 6 compactified into intricate shapes like Calabi-Yau manifolds, folded geometries tinier than any probe. These extra dimensions aren't fanciful. They explain why gravity seems weak compared to other forces, diluted across the full space. Metaphors help. Think of strings as guitar strings. Different notes, vibrations, produce different particles, harmony from a single instrument. Or Plato's cave. We see shadows of higher dimensional reality projected onto our 4-dimensional wall. Dualities abound. T-duality swaps small and large radii. S-duality, strong and weak coupling, revealing that 5 seemingly different string theories are facets of one underlying M theory in 11 dimensions. The ambition is breathtaking. Unify all forces, explain particle masses and couplings from geometry, perhaps derive the Standard Model itself. Yet the landscape problem haunts it. Those 10⁵ vacua aren't a bug. They're a feature of the compactifications. Each shape yields different physics, populating the multiverse we met earlier. String theory doesn't predict unique constants. It allows almost anything, with anthropic selection picking ours. For proponents, this richness is a clue. The theory is flexible enough to encompass reality. Critics see it as a curse. Too many possibilities, too few unique predictions. After decades, no direct experimental signature. No supersymmetric partners at LHC energies. No extra dimensions glimpsed. Yet indirect tests loom. Precision CMB measurements, gravitational wave signatures of phase transitions, or cosmic strings as linear defects. String theory remains the most developed candidate, a symphony waiting for its final movement. Yet string theory's greatest rival took a different path entirely. Space itself might be made of indivisible grains, and the singularity nothing more than an illusion of classical equations. While string theory builds from vibrating objects in fixed backgrounds, loop quantum gravity, LQG, takes the opposite tack. Quantize space-time itself background independently, directly from Einstein's equations. Born in the late 1980s through the work of Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, LQG rephrases general relativity in terms of connections rather than metrics, variables akin to electromagnetic potentials. Quantizing these yields spin networks, graphs where nodes and links carry quantum numbers of area and volume. Space emerges from these networks, not continuous but discrete, woven from Planck scale loops. Picture atoms of geometry. The smallest possible area is about the Planck length squared. Volume comes in quantized chunks. Smooth space-time is a large-scale approximation, like water appearing fluid despite molecular discreteness. This quantization banishes singularities. In the Big Bang, as density rises, classical collapse halts when quantum geometry repels. The universe reaches a minimum volume and bounces, echoing the cyclic models we explored earlier. Cosmological simulations in loop quantum cosmology, LQC, show a pre-Big Bang contracting phase, symmetric to our expansion, connected smoothly through the bounce. Black holes fare similarly. At the core, where classical theory predicts infinite curvature, quantum effects dissolve the singularity into a finite density region. Information paradox resolves. Horizons become dynamic. Tunneling allows leakage, or the interior transitions to a white hole phase. Recent models suggest black hole remnants, Planck-sized relics that preserve information without evaporation paradoxes. LQG is rigorously background independent, no fixed space-time assumed, geometry dynamical from the start. This aligns deeply with general relativity's spirit, unlike string theory's reliance on extra-dimensional backdrops. It predicts testable signatures, modified dispersion relations for light from distant gamma-ray bursts, or CMB anomalies from bounce-era physics. Progress has been steady, but slow. Exact dynamics, the Hamiltonian constraint, remain thorny. Full transition amplitudes between spin networks are computed only in simplified cases. No unification of forces yet. Matter couplings are added by hand. Critics argue it lacks the richness of string theory's dualities and particle predictions. Yet for many, LQG's directness appeals. No supersymmetry assumed, no landscape proliferation. It offers a universe where quantum gravity is discrete and relational, time and space emerging from relations between events. Both approaches promise to resolve the beginning, but neither has yet delivered a definitive picture. After half a century, the marriage of quantum theory and gravity remains unconsummated. String theory and loop quantum gravity dominate the landscape, but they are not alone. A vibrant ecosystem of alternatives thrives, each attacking the problem from unique angles, reminding us that consensus remains elusive. Asymptotic safety, pioneered by Steven Weinberg in the 1970s and advanced by Christoph Wetterich and Martin Reuter, seeks a non-perturbative ultraviolet fixed point in gravity's renormalization flow. Pure quantum gravity might be finite and predictive without new ingredients, No strings, no loops, just Einstein's theory rendered safe at high energies via interacting fixed points. Calculations suggest a four-dimensional theory with few parameters. Recent results hint at compatibility with observed particle masses and cosmology. Causal set theory from Raphael Sorkin and others posits space-time as a discrete set of events ordered causally. Random sprinklings into Minkowski space, grown dynamically, approximate continuum geometry. The approach is background independent and predicts Lorentz invariance as emergent. Challenges include recovering full general relativity and explaining entropy. Emergent gravity views space-time itself as arising from deeper principles. Eric Verlinder's entropic gravity treats it as thermodynamic, like elasticity from molecular motion, dark energy from entanglement entropy. Juan Maldacena's Adi as Asis CFT correspondence inspires holography. Our universe as a projection from a lower dimensional boundary theory. These ideas blur the line between fundamental and derived. Group field theory and tensor models blend LQG's spin foams with string-inspired combinatorics. Quantum graphity imagines space-time condensing from a pre-geometric phase. Even revived ideas like twistor theory from Roger Penrose recast space in terms of light rays and conformal structures. The diversity is both strength and weakness. Each approach resolves some paradoxes, singularities, information loss, the measure of time. But none has achieved the Holy Grail, a complete, testable theory matching all observations from Planck scale to galaxies. Experiments remain indirect. No Planck energy accelerators exist. We hunt for echoes in the CMB, gravitational waves from phase transitions, or quantum optics tests of entanglement in curved space. Half a century since the quest intensified, quantum gravity remains a mosaic of promising fragments. No single picture commands allegiance. Debates rage over background independence, discreteness versus continuity, unification versus emergence. The field's openness reflects physics at its healthiest. Bold ideas competing, awaiting the crucial observation or mathematical breakthrough. And so we return to the ancient silence with which we began. Older questions, new whispers. Change the strength of gravity by 1 part in 10 mul 40, and stars never form. Life becomes impossible. Why is the dial set exactly where it is? We have journeyed far, from the accidental discovery of the universe's afterglow to the explosive stretch of inflation, from eternal multiverses to bouncing cycles and colliding brains. Telescopes have shown us a cosmos older and stranger than we imagined. Quantum gravity theories have sketched possible resolutions to the singularity. Yet beneath every explanation, every revision, one mystery has persisted, quiet but unrelenting. The exquisite fine-tuning of the physical constants themselves. Consider the constants that govern reality, not derived quantities, but the fundamental dials of nature, numbers that could, in principle, take any value, yet appear calibrated with almost inconceivable precision for the existence of complexity, chemistry, and life. start with gravity. The gravitational constant G sets the strength of attraction between masses. If G were stronger by even 1 part in 10^40, a 1 followed by 40 zeros, stars would burn hotter and faster, collapsing into black holes before planets could form or chemistry could unfold. Weaken it by a similar fraction, and gravity could never pull gas clouds into stars at all. The universe would remain a diffuse soup of hydrogen and helium, dark and sterile. The electromagnetic force, governed by the fine structure constant. 137 balances repulsion between protons and attraction to electrons. Increase SR by a few percent, and hydrogen atoms become unstable. No water, no organic molecules. Decrease it slightly, and electrons bind too weakly. Atoms grow too large, chemistry too sluggish for complex compounds. Carbon, the backbone of life, forms in stars via the triple alpha process, a resonance where 3 helium nuclei fuse. This resonance depends on the strong nuclear force constant, shifted by less than 1%, and carbon production plummets, or oxygen dominates instead. The Higgs field gives particles mass via its vacuum expectation value. Too high a value, and all particles become too heavy. Atoms cannot form. Too low, and protons decay or electrons escape nuclei. The cosmological constant L, once thought 0, is measured at about 10^120 in Planck units. Tiny, but positive. Make it larger by a factor of 10, and expansion accelerates too violently for galaxies to coalesce. Make it negative and large, and the universe recollapses instantly. These are not isolated cases. The weak force, neutron-proton mass difference, quark masses, all sit in narrow windows permitting stable nuclei, long-lived stars, and the periodic table. Change several together, and the allowed range shrinks further. Cosmologists calculate the habitable fraction of parameter space. In many models, it is less than 1 part in 10, 100 or smaller. Randomly chosen constants almost always yield universes that are empty, short-lived, or structureless. The numbers are vertiginous. Physicists speak of them with a mixture of awe and unease. Martin Rees, in his book Just 6 Numbers, highlighted how slight variations erase the possibility of observers. Leonard Susskind called fine-tuning the most unnatural natural thing in physics. The constants seem less like arbitrary inputs and more like a delicate setup, balanced on a knife's edge across multiple dimensions. Why? The question hangs in the air, unyielding. In a universe governed by impersonal laws, why do the dials align so precisely for complexity? Why not values that produce only black holes, or endless radiation, or nothing at all? Some accept the multiverse, others seek deeper laws. We searched for a reason the constants must be as they are, and found only silence. Faced with fine-tuning, physicists have long hoped for a deeper principle, a law or symmetry that forces the constants to their observed values, rendering them inevitable rather than accidental. One early hope was naturalness. Quantum corrections should not require enormous cancellations unless protected by symmetry. The Higgs mass, for instance, receives huge radiative contributions from high scales, yet remains light. Supersymmetry was proposed to pair bosons and fermions, cancelling divergences, predicting partner particles at TeV energies. The LHC found none. Supersymmetry may exist at higher scales, but the required tuning to hide partners is itself unnatural. Grand unification sought to merge forces at high energy, relating their strengths via group structure. Simple SU5. Models predicted proton decay too rapid. Experiments ruled them out. Larger groups like SO10 survive, but require intermediate scales and additional tuning. String theory promised uniqueness. Early excitement centered on heterotic models or specific Calabi-Yau compactifications yielding the standard model. Yet the landscape revealed the opposite. Vast numbers of vacua, no principle selecting one. Attempts to find preferred regions via flux stabilization or statistical measures remain inconclusive. Asymptotic safety in gravity or other non-perturbative mechanisms might fix couplings at an ultraviolet fixed point. Promising calculations exist, but connecting to particle physics remains distant. Other ideas flickered brightly, then dimmed. Technicolor aimed to generate masses dynamically without a fundamental Higgs. LHC data favored the elementary scalar. Scale invariance or conformal symmetry at high energy might forbid certain parameters. Anomalies and dark energy complicate this. Even cosmological selection, universes evolving constants via varying laws, struggles with predictability and the origin of variation itself. One by one, promising paths have narrowed or stalled. No symmetry has emerged to dictate R equals 1 on 137. No dynamical mechanism robustly sets L to 10/120. The hierarchy problem, why gravity is 1040 times weaker than other forces, remains unsolved without fine-tuning or new physics beyond reach. The silence is profound. Decades of effort have yielded deeper theories, richer mathematics, but no compelling reason why the constants must be life-permitting. Some speak of a desert, a high-energy landscape devoid of new physics that would explain the tuning. Others worry the problem lies beyond current paradigms. Perhaps the answer lies not in physics alone. In the end, every origin story returns us to the same place, a silence that invites wonder, dread, or both. With physical explanations faltering, the fine-tuning mystery spills beyond the laboratory into philosophy, theology, and speculation. Human minds, confronted with the same improbable dials, have responded in strikingly different ways. One ancient response is theistic. The constants reflect design, a purposeful intelligence setting the parameters for a universe capable of life and mind. Proponents point to the specificity, how even slight changes erase observers, as evidence of intent. Critics counter that invoking a designer merely shifts the question: who or what tuned the designer? Yet for many, fine-tuning revives the argument from design in modern form, a cosmos appearing engineered for discovery. Another contemporary idea is the simulation hypothesis. We inhabit a computed reality run by advanced posthumans or higher beings. Constants are parameters in code, tuned for interesting outcomes, perhaps to study life or run ancestor simulations. The notion draws from computing power trends and philosophical puzzles about consciousness. Detractors note its unfalsifiability and the infinite regress of simulators simulating simulators. A third stance embraces pure contingency. The constants are brute facts, unexplained and perhaps unexplainable. Physics describes but does not ultimately explain why. In this view, fine-tuning is a selection effect. We can only observe values permitting observers, without needing multiverses or design. The universe simply is. Its dials set by chance or necessity we cannot access. Multiverse proponents, as we have seen, treat fine-tuning as environmental. In an infinite ensemble, life arises only in the rare tuned pockets. This preserves naturalism, but at the cost of testability and uniqueness. Each perspective carries emotional weight. Design offers purpose, but challenges secular worldviews. Simulation fascinates, but risks nihilism. If reality is code, what is real? Contingency humbles, reminding us of limits. Multiverse explains but dissolves specialness. No consensus binds them. Scientists hold all views privately. Public discourse often sidesteps the philosophical depth, yet the mystery endures, shared across cultures and eras. Why something rather than nothing? And why this something? We began with silence, the vast cosmic hush pierced by a faint microwave whisper. Every theory, every observation has led us back to a deeper quiet, the unexplained precision underlying all existence. Whether we answer with law, chance, design, or acceptance, the silence remains, an invitation to wonder at our improbable presence in a universe that permits wondering at all. And so we stand at the edge of knowledge, listening for echoes that may never come. We have traveled from campfire tales to instruments orbiting beyond the moon, yet the first moment remains veiled. We began in silence, an invitation to close our eyes and listen to the vast, empty dark. From there, we traced humanity's long arc of questioning. Ancient myths of cosmic eggs and primal voids, giving way to careful measurements of light and elements, red shifts and ripples. We met the accidental discoverers scrubbing pigeon droppings from an antenna, only to hear the universe's oldest whisper. We followed the pillars of the Big Bang, its afterglow, its primordial chemistry, its grand expansion, only to find shadows lurking in the perfection. Horizons that should never have aligned, flatness balanced on an impossible edge, missing relics that theory demanded. Inflation arrived like a sudden wind, stretching the infant cosmos exponentially, smoothing and flattening and cleansing in one bold stroke. Yet it carried us further than intended, into eternal bubbling, a multiverse of infinite possibilities where our constants are mere environmental happenstance. alternatives rose to challenge it. Universes that bounce through quantum repulsion, eons linked by conformal rescaling, brains colliding in higher dimensions. Telescopes pierced the dawn, revealing galaxies too mature, black holes too greedy, expansion rates that refuse to agree, cracks widening in the story we thought settled. Quantum gravity offered competing visions, strings vibrating in hidden dimensions, loops weaving discrete space-time, emergent geometries and causal sets. Fine-tuning persisted, a quiet enigma, dials set with precision that defies chance yet eludes explanation. We weighed multiverses against design, simulation against contingency, finding no final verdict. Now, as our journey nears its close, let us look ahead. The quest continues, lanterns glowing brighter in the fog. CMB S4, an array of telescopes at the South Pole and in Chile's high desert, will map the microwave sky with unprecedented precision, hunting for primordial gravitational waves, the curled ripples from inflation itself. Euclid, already orbiting, charts billions of galaxies to probe dark energy's evolution. The Laser Interferometer Space Antenna, LISA, set for the 2030s, will listen for low-frequency waves from supermassive black hole mergers in the early universe. 30-meter class ground telescopes, the extremely large telescope, the Giant Magellan, the 30-meter telescope, will resolve individual stars in distant galaxies, tracing the true timeline of cosmic dawn. Simon's Observatory and Lightbird refine polarization patterns. Next-generation surveys like the Rubin Observatory scan the sky nightly for transients. Gravitational wave detectors, upgraded LIGO, Virgo, Kagra, and future Einstein telescope catch echoes of neutron star collisions and perhaps phase transitions from the universe's youth. These instruments promise sharper views, better constraints on inflation's energy scale, tighter limits on neutrino masses, direct images of exoplanets around ancient stars. They may confirm or falsify signatures of bounces, brain collisions, or stringy effects in the CMB. They will measure the Hubble tension with exquisite accuracy, perhaps revealing new physics in the late universe. Yet for all their power, they probe only what light and waves can carry across 13.8 billion years. The first instant, the true origin, lies behind inflation's veil or quantum gravity's horizon. Whatever future data bring, some questions may persist. There may be truths forever beyond our reach, not because we are small, but because the universe is vast in ways we cannot imagine. Science thrives on boundaries pushed ever outward, yet some frontiers may be absolute. The observable universe is finite, bounded by the distance light has traveled since the beginning. Beyond lies more of the same, perhaps infinitely, but causally disconnected forever. If inflation is eternal, countless bubbles bloom beyond our horizon, their laws unknowable. We are islands in an endless sea, able to map our shores, but never the full ocean. Even within reach, information erodes, Black holes swallow details, evaporating slowly via Hawking radiation that scrambles quantum data. Though unitarity promises preservation in principle, reconstruction may be impossible for any observer. Singularities, if they exist, erase histories entirely. The pre-inflationary patch, smaller than a proton before its explosive stretch, leaves no direct imprint. Quantum fluctuations dominate, washing away prior structure. The question of before may be meaningless. In classical relativity, time emerges with space-time. Asking what preceded the Big Bang is like asking north of the North Pole. Quantum cosmologies, no boundary, tunneling from nothing, render the origin timeless, a geometry without edge. Bouncing models carry echoes forward, but infinitely many cycles backward dissolve into quantum fuzz. Why the laws are as they are, why these constants, this dimensionality, may lie outside empirical grasp. If a multiverse explains fine-tuning anthropically, we cannot survey the ensemble. If a unique theory awaits, its selection principle might require mathematics beyond our cognitive reach. Gödel's incompleteness reminds us even formal systems harbor unprovable truths. These limits are not failures, but features. Science describes the accessible, predicts the testable, refines the approximate. Some questions, why something rather than nothing? Why this something may transcend method, belonging to philosophy or contemplation. Accepting unknowability need not diminish wonder. It deepens it. The universe's vastness includes realms we can only gesture toward, truths that shape us without revealing themselves. Humility before the unknown has driven discovery since antiquity. Admitting boundaries frees us to cherish what we do know. A cosmos 93 billion light-years wide, born 13.8 billion years ago from a hot, dense state, evolving through gravity and light into galaxies, stars, planets, life, minds capable of reconstructing the tale. Embracing uncertainty can be profound, a quiet acknowledgement that reality exceeds our grasp, yet invites endless approach. And still we ask, close your eyes again. The silence is still there, waiting, and somewhere within it, the universe began. We return, full circle, to the beginning. The faint hiss of the cosmic microwave background fades in once more. Real recorded static, soft beneath my words. Listen. It is the same whisper Penzias and Wilson stumbled upon, the same glow filling every direction, the afterheat of creation stretched across billions of years. Whatever story resonates with you, Big Bang evolving smoothly from inflation's burst, eternal cycles rebounding through quantum grace, brains colliding in hidden dimensions, a multiverse bubbling endlessly, or simply a profound mystery beyond resolution. The act of wondering binds us to every human who has ever tilted their face to the night. From ancient stargazers weaving constellations into myth, to medieval scholars charting heavenly spheres, to astronomers today aligning mirrors under desert skies, we share the same impulse, to make sense of the lights above. to find our place in the vastness. The questions evolve, instruments sharpen, theories rise and refine, yet the core remains. How did it all begin? Why are we here to ask? No final answer may come. The silence endures, patient and deep. It holds the echo of the first light, the memory of forged elements, the rhythm of expansion. It cradles galaxies spinning in darkness, worlds turning under alien suns, perhaps other minds gazing outward in their own wonder. You, listening now, are part of this lineage. Your curiosity, quiet or urgent, connects you across millennia. Whether you find meaning in equations, in cycles eternal, in a multiverse's lottery, in design or pure contingency, the wondering itself is the gift. It turns emptiness into awe, isolation into belonging. Close your eyes once more. Let the night sounds rise, wind through leaves, distant waves on a shore, the soft rush of breath. Beneath them, the universe's whisper persists, unchanged. Somewhere within that silence, everything began. And somewhere within it, we continue. The hiss lingers alone now, fading slowly into natural quiet. No voice returns. Only the invitation remains. Keep listening. The answers may not arrive all at once, but the act of wondering changes us. If tonight's journey stirred something in you, let it settle gently. Thank you for listening. This has been the calm unknown. Rest well and keep wondering.